Every time you press the accelerator, controlled explosions reaching 2,600 degrees Celsius and 15 megapascals of pressure erupt inside a metal block inches from your legs, thousands of times per minute. That's how your car engine really works. Not as a simple machine, but as a violently precise chain reaction where everything depends on what happens inside a single cylinder, across 4 exact strokes. Inside a single cylinder, 4 distinct strokes unfold in perfect sequence. The first is intake. As the piston moves downward, the intake valve opens, and a rush of air, often at rates approaching 550 cubic feet per minute in high-output engines, sweeps in, carrying with it a finely atomized mist of gasoline. This incoming charge fills the combustion chamber, drawn in by the low pressure created as the piston descends. Next comes compression. The intake valve closes and the piston rises, squeezing the air-fuel mixture tightly into the top of the cylinder. Pressures climb rapidly, reaching around 12 megapascals, while temperatures soar to roughly 650 Kelvin. This dense, hot mixture is primed for ignition, but timing is everything. At the top of this stroke, the spark plug fires. The ignition event itself lasts just fractions of a millisecond, but it sets off a rapid flame propagation about 40 meters per second across the chamber. The chemical energy of the fuel is unleashed, and pressure spikes to a peak of 15 megapascals. Temperatures inside the cylinder can hit 2,600 degrees Celsius. The expanding gases force the piston down in the power stroke, delivering the mechanical punch that turns the crankshaft. Finally, the exhaust stroke begins. The exhaust valve opens, and the piston climbs back up, pushing out the spent gases. A vacuum forms behind the departing gases, dropping pressure to around -10 kilopascals, helping to scavenge the cylinder for the next cycle. Each of these 4 strokes must occur in precision order and at exact intervals. The process repeats thousands of times per minute, ensuring that every cylinder fires in perfect rhythm, setting the stage for the synchronized firing order that keeps the engine running smoothly. Each piston's downward surge is only the beginning. In a 4-cylinder engine, the sequence follows a strict 1-3-4-2 firing order. This pattern isn't arbitrary, it's engineered to distribute the bursts of power as evenly as possible, smoothing out the delivery of torque. When cylinder 1 fires, the others are at different points in their cycles, and within milliseconds, cylinder 3 is ready to ignite, followed by 4, then 2. This choreography reduces the peaks and valleys in the engine's output, minimizing what engineers call torque ripple. At 7,000 revolutions per minute, each cylinder's contribution overlaps, allowing the crankshaft to spin with less than 0.02 G of vibration, barely enough to register on sensitive instruments. The crankshaft itself is the engine's mechanical heart. Its throw, typically 45 millimeters in a modern 4-cylinder, acts as a lever arm for each piston's force. As the connecting rod pushes down, the crank converts that force into rotational movement. This up and down motion, repeated thousands of times per minute, becomes a smooth, continuous spin. Counterweights, precisely shaped and balanced, are built into the crankshaft to tame the natural imbalance created by the piston's rapid acceleration and deceleration. Without them, the engine would shake itself apart at high speed. This system links each isolated combustion event into a unified, stable rotation. The result is a steady flow of torque that drives the flywheel, transmission, and ultimately the wheels. The firing order, crank geometry, and counterweight balancing work together to turn a series of violent explosions into the smooth, reliable motion that defines the modern automobile. The camshaft serves as the engine's timing maestro, orchestrating the movements of the intake and exhaust valves with exacting precision. Each cam lobe is shaped to a specific profile, dictating not only how far a valve opens, its lift, but also how long it stays open, known as duration. In a typical modern engine, intake valve lift reaches up to 9 millimeters, allowing a substantial volume of air to enter the combustion chamber. The moment when the valve begins to open is just as critical. Intake valves often start to lift around 12 degrees before top dead center, ensuring that airflow is ready as the piston descends. As the camshaft rotates, its lobes press against lifters or rocker arms, translating rotational motion into the linear movement that opens each valve. The duration that a valve remains open is carefully calibrated for the engine's needs at different speeds. Overlap, the brief window, when both intake and exhaust valves are open, lets the outgoing exhaust pulse help draw in fresh air. But too much overlap can reduce low-speed efficiency. Every aspect of the cam lobe's geometry is engineered for a precise balance between power, efficiency, and emissions. The camshaft's rotation is synchronized with the crankshaft by a timing chain or belt, which must maintain accuracy within fractions of a percent. Chain stretch beyond 0.02% can disrupt valve events and compromise performance. This mechanical choreography ensures that every stroke receives the right charge of air at exactly the right instant, setting the stage for precise fuel metering and the next phase of the engine's cycle. The moment air rushes into the cylinder, the engine's electronic control module takes over, calculating exactly how much fuel is needed for the next combustion event. At the heart of this process is the fuel injector, a solenoid-driven valve capable of delivering a shot as small as 200 micrograms of gasoline in a single cycle. The injector's opening time, its pulse width, can be as brief as 0.5 milliseconds at idle, stretching to 4 milliseconds under heavy acceleration, but typically hovers near 1.5 milliseconds during normal driving. For each injection, the ECM references a continuous stream of data: air mass, intake temperature, engine speed, and oxygen sensor readings. The goal is to maintain a stoichiometric air-fuel ratio of 14.7 to 1, ensuring complete combustion and minimal emissions. Airflow is measured by a mass airflow sensor, which keeps error below 2% across the load range. If a deviation is detected, the ECM adjusts the next injector pulse in as little as 0.1 seconds, fast enough to respond to a sudden change in throttle. This closed-loop feedback system means that every cylinder, every cycle, receives a digitally calibrated dose of fuel. Even as engine speed and load fluctuate, the injector's precision and the ECM's rapid adjustments keep combustion balanced and consistent, laying the foundation for the engine's thermal and lubrication demands in the next phase. Combustion inside the cylinders produces a constant surge of heat, far more than the engine's metal can tolerate on its own. To keep temperatures in check, a dedicated coolant circuit moves through the block and cylinder head, absorbing excess thermal energy. The water pump circulates coolant at rates up to 30 liters per minute, maintaining a pressure near 1.4 bar to prevent boiling even as coolant snakes pass the hottest surfaces. Once the fluid exits the engine, it travels through the radiator, where thin metal fins and a steady rush of air strip away heat. The thermostat, set to open at 92 degrees Celsius, keeps the engine within its optimal range, closing off flow when cold and opening fully as temperatures climb. This system ensures the engine operates efficiently without risking heat damage or warping vital components. While the coolant circuit manages thermal loads, the alternator manages electricity. Driven by a belt from the crankshaft, the alternator spins a rotor inside a coil, generating alternating current that is rectified to deliver a steady 14 volts. This output, often rated at 50 amperes or more, powers the ignition, fuel injectors, sensors, and every electronic system in the vehicle. The spark plug's demand is especially intense. The ignition coil transforms the alternator's low voltage into a surge of up to 30,000 volts, enough to jump the plug gap and ignite the compressed fuel-air mixture. By keeping voltage and current stable, The alternator and coil ensure that each combustion event fires on schedule, supporting both performance and reliability as the engine runs hour after hour. Inside the engine, a thin oil film measured at just 15 micrometers coats every moving surface, from crankshaft journals to cam lobes. This layer does more than reduce friction. It acts as a heat sink, drawing excess warmth away from bearings and piston skirts and forms a dynamic seal that helps contain combustion pressure. Modern oil is engineered with a viscosity index near 150, which means its thickness stays stable as temperatures swing from cold starts to peak load. Additives make up about 2% of the oil's volume, with detergents suspending soot and metal particles, while 3% zinc dialkyldithiophosphate, or ZDDP, guards against wear and corrosion. These chemical agents keep sludge from forming and protect critical surfaces, even as the engine cycles through thousands of revolutions per minute. As combustion gases exit the cylinders, they carry a mix of carbon monoxide, unburned hydrocarbons, and nitrogen oxides. The catalytic converter stands as the final barrier. Inside, a ceramic honeycomb is coated with a blend of platinum, palladium, and rhodium, about 300 grams in total for a typical car. When exhaust temperatures reach 250 to 300 degrees Celsius, these precious metals trigger chemical reactions that convert over 95% of carbon monoxide and hydrocarbons into carbon dioxide and water, while slashing nitrogen oxide levels. This aftertreatment keeps tailpipe emissions within strict regulatory limits, ensuring that the engine's power comes with minimal environmental impact. The combined effect of oil's five-fold protection and the catalyst's efficiency allows the modern engine to operate cleanly and reliably, cycle after cycle. Every revolution under your hood is a product of engineering precision, timing, temperature, and chemistry in exact balance. As vehicles evolve with hybrid and electric powertrains, understanding these fundamentals remains critical. The principles of combustion engines still shape mobility decisions, efficiency standards, and the future of transportation. Thanks for watching.